Thank you for got it. So thank you. I'm Alessandro, and this is the plan for this talk. I will first recap the basics of gravitational waves and how we detect them, and then introduce a bit the astrophysics of gravitational waves, so the formation scenarios and which observational signatures we can extract from the waves. Then introduce the topic of gravitational waves from active galactic nuclei, and then just briefly mention some outlooks and some other work I do besides gravitational waves. And also, please let me know if you can hear me correctly, and if the signal stops, just
Okay.
yeah, make some noise.
Okay.
And so, first of all, as you probably know very well, gravitational waves are a prediction from general relativity. The source of gravitational waves is an accelerating mass quadrupole moment, and the simple source that we can imagine is the 2-point masses on a circular orbit. Astrophysically speaking, these are two, it's a black hole binary, circular black hole binaries. Such a source will emit and radiate gravitational waves at twice the orbital frequency of the binary. And as energy is radiated, the binary shrinks and in spirals until we have a coalescence and a bigger black hole is formed. If we were to visualize the effects of gravitational waves as they move through time-space, we could see through a simple experiment. Imagine there is a ring of test masses in the plane of the screen. There is a gravitational wave coming through the plane, and we would see this kind of oscillations. So we would see the distance between these test masses change, contract, and dilate, and we would see this kind of oscillations corresponding to different polarization of the wave. So how we detect this kind of change in distance is through laser interferometry. So this is a very basic system, classic system, the microsol interferometer. So basically monitoring the distance into big arms by looking at the interference of a laser wave that is being split and then recombined. And by measuring the interference pattern, one can monitor the distances into to the two arms. This has been this is basically the basic physics behind the gravitational wave detectors. We have at the moment 4 gravitational wave detectors run by the LIGO-Virgo-Kagra collaboration. This is the 4 main detectors. 2 are in US, 1 is in Italy, and the 4th one is in Japan, in the Kamioka mines next to the neutrino experiments. And I'm actually part of the Kagra collaboration, the theory group. And yeah, Kagra is the latest detector to have seen the light, or rather the gravitational waves. Unfortunately, its sensitivity is not yet sufficient because it's just the latest arrival, but implements already 2.5 generation technology in the form of cryogenic sapphire mirrors. So, and there is also LIGO India planned and new detectors to improve, let's say, possibility of detection. And as I mentioned earlier, the gravitational waves have a frequency, so there is a spectrum of gravitational waves. At the moment, we are here, so we observe at the high end of the spectrum, very high frequencies, and with terrestrial interferometers. Last year, we had some announcement from the PTA collaboration of the evidence of a gravitational wave background, and this is measured with pulsar timing arrays, and it's basically monitoring the change in pulsar timing arrival from different pulsars in the sky, and this will change if there is a gravitational wave passing between us and the pulsars. And so if we measure some correlation in the pulsar timing delay, then we can measure this gravitational wave background. But we are talking about much larger waves due to supermassive black hole binaries, so no stellar mass black holes. And of course, in the future, there will be also space interferometers, such as the these satellites. And this will be able to measure more massive sources, so supermassive black hole binaries that reside at the center of galaxies at much lower gravitational wave frequencies. At the moment, I will focus just on this last part. This is the first detection of gravitational waves. This is how it looks like, the signal in probably in a reconstructed way. And the first thing that you notice that the signal is quite short in time. This is a fraction of a second. And the reason why is at these frequencies, we don't have any monochromatic sources. What we can capture with ground-based detectors is the last instance of the spirals of a binary. And we say that the signal is chirping, which means it crosses several frequencies. And you can see that so this is the expression of the derivative of the frequency as it sweeps to the frequencies until it spirals and you have the merger event. If we measure the derivative of the frequency and the frequency itself, we can measure what we call this chirp mass, which determines basically how the signal evolves through the frequencies. And with higher Poissonian correction, it is possible also to measure the reduced mass, thereby breaking the degeneracy between the two masses. So we can have an idea of what the two masses of the merging objects are by analyzing the signal. After this detection, like 8 years ago, at the moment, there is still ongoing the 4th observation run. So we have a total of about 100 events that have been detected so far. Most of these events involve black holes, so binary black holes that coalesce. A few of them involve binary neutron stars, and a few of them, maybe one of them, has a neutron star black hole merger. And here in this plot, you can see basically all the events so far, compared to also black holes and neutron stars observed via electromagnetic observations, which means mostly by astrometry. For example, if there is a star that is orbiting an unseen object, then it's possible to infer the mass of this black hole, or through, well, pulsars and through accretion, so black holes that are accreting from a companion star. You can see immediately that, first of all, we are much more sensible to louder mergers, so higher masses of the black hole. So we actually probe a different region of the black hole mass spectrum, if you want to call it like this, with EM observations and gravitational wave observations. And of course, this is a huge potential for new discoveries. One can test general relativity and alternative theories of gravity with gravitational waves. They can also be used as cosmological sirens, especially if there is a EM counterpart that we can use to break the redshift, that we can use to measure the redshift, basically. And also to solid state physics to probe the equation of state of neutron star that will have tidal deformation that we can see on the waveform. And my angle as the one of many astrophysicists is to use gravitational waves as a way to probe astrophysical environments. And to do this, so this is, of course, a very powerful tool, but it's important to remember that gravitational waves are very different from EM, electromagnetic waves. And first of all, in nature, we measure the wave amplitude called strain, not the power, or we don't count photons, or you don't count the gravitons, or just like we count photons on a CCD. But the second most important point is that we can see only we expect to see, and to observers, I make often the analogy of being able to observe supernovae, which are another kind of transient event that we observe in the optical, but only if we know the light curve a priori. And the reason for this is that in order to detect gravitational waves, we need to use a technique called match filtering, which is basically boils down to convolving a known signal into the noisy data of the detector. And from this animation, you can see as we convolve the signal, then if there is an underlying signal in the noisy data, you can see a spike in the signal to noise ratio. So what does this mean is that it's theoretical predictions on the waveform are crucial to extract the signal, and astrophysical priors of the template bank of waveforms will impact the detectability of gravitational wave events. And it's for example, the very first signal was missed by all searches because, but the one that was basically agnostic with respect to the sort of properties. It just measured let's say the coherence and coincidence of different detectors at the same time. And the reason is that because they lacked masses above 10 solar masses. And the first event involved 2 black holes of 30 solar masses, just because we have wrong astrophysical priors. So theory is quite important. And if we know the signals, it's possible we generate different signal and different waveforms, different templates. It's possible to extract from the waveform these kind of variables about the sources. So we can now infer the masses of the two. I call them black holes, but there can be also neutron stars, of course. The spins of these black holes and their orientation. And this doesn't come just like this. Actually, it's a bit more degenerate with masses and also with the obliquity of the spin, which is the angle between the binary angular momentum and the spin vector. Of course, we can infer the merger rate, which at the moment sits in this range. In principle, we would be able to detect the eccentricity of the sources. So I mentioned at the beginning that we have circular binaries, but this is just a simplification. Unfortunately, at the moment, it's quite difficult to detect the eccentricity in the late spiral phase. One reason is that gravitational wave radiation tends to circularize the binaries. And by the time they merge, they're most likely quite circular. And the second reason is that we still don't have templates, gravitational wave templates that include both spins and eccentricities. And these two can introduce degeneracies. So there's some degeneracy between these two effects. So we really need both effects in the same gravitational wave surrogate. Yeah. And the third, the final aspect is that the distance and localization at the moment is not great with only 3 detectors. We are limited to, let's say, up to 1.5 redshift. So we're limited just to observe gravitational waves in the local universe with very large uncertainties. And the sky localization, it's quite poor because of having only 3 detectors when Virgo can detect. And so most of the time, just the 2 LIGO ones. So it's quite difficult to understand what is the astrophysical source, the astrophysical environments from which these events come from, just by looking at individual events. But it's possible, as we build up a catalog of transient events, it's possible to use population properties in order to understand where these gravitational wave events come from. And so far, there have been a lot of formation channels proposed. This is a scheme that illustrates the main the categories of astrophysical formation channels. Of course, we also have non-astrophysical formation channels in the form of primordial black hole. I won't discuss this. And we can broadly categorize these two in a isolated binary evolution. So when you have a binary that forms, instead of forming a single stars from a collapse of a molecular cloud, you have a binary. And then this binary interacts through processes like mass transfer events or common envelope events, which is where 2 stars are engulfed by the common envelope of a giant star. And then you have also dynamics, which involves dynamical interactions between black holes in dense stellar environments like globular clusters, neutron star clusters, young star clusters. And then you have intersection between these categories like stellar triples, which evolve through dynamics, but also through stellar evolution processes. And of course, active galactic nuclei, which I will discuss later. So I am a dynamicist, so my main interest is in this red region here, but I have also worked on isolated binary evolution, and my main interest is in this sense is to modeling the non-Newtonian part of the evolution of a binary, which includes interactions with the common envelope, so with, say, background gas, gaseous medium, or tidal evolution of two close stars, which is important to, for example, produce spin, say spin-up stars, and maybe impart a spin, primordial spin to the black holes they form. I will just mention in this presentation, I will just describe what is this active galactic nuclei channel. Yeah, active galactic nuclei, first of all, are these very bright sources in the sky. We think they're powered. They're basically a supermassive black hole that is powered by an accretion disk. Accretion disk is hot, so it emits over the continuum. It can be seen of many electromagnetic frequencies. The observational feature of this kind of objects changes depending if if the observer is located towards the jet, or there is the obscuring torus that changes the properties of the signal that arrives to us, and they're central to galaxy evolution and astroparticle physics and so on. And in the recent, let's say, couple of years, they have been proposed as factories for gravitational wave mergers of stellar mass black holes. So not the supermassive black hole at the center, but stellar mass black hole that live in the neighborhood. And actually, it's not IGNs are not this kind of channel is not the only one. In regards to gravitational wave from IGNs, IGNs have been already proposed as a source of other kind of gravitational wave, especially in the LISA band and also in the PTA band. In the sense that if you have not a single black hole, but you have a binary supermassive black hole, like in this picture here, you have kind of binary disk interactions. The disk basically can torque the binary and speed up the merger, the coalescence of the supermassive black hole binaries. Another kind of interesting sources are extreme mass ratios in spiral. Here, the extreme mass is due to the fact that a stellar mass black hole is spiraling onto the supermassive black hole. But what I mean by IGN channel is this one. So when you have mergers between stellar mass black holes in the LIGO band, so high frequency, and where the gas-rich condition can facilitate the merger of binaries that are embedded into the disk. So a very kind of short story of how this AGN channel works is the following. So first of all, we need to imagine that supermassive black hole resides at the center of galaxies, and by dynamical processes like two-body relaxation, so long-range gravitational interactions between the stars, black holes, so the most massive objects, tend to sink toward the center of the galaxy and form a cusp of black holes. These are prediction of theories, the prediction of the theory. And it might be also corroborated by observation in our galactic center, where we have a supermassive black hole of 10 to the 6 solar masses. And there is some hint that low mass X-ray binaries may actually trace a cusp of black holes around the supermassive black hole around our supermassive black hole. Yeah. So if this supermassive black hole, if this galactic nucleus becomes active, so a disk of gas forms around, probably due to galaxy merger, or maybe even a kind of that gas dynamics instability in the galaxy. There is an inflow of gas and disk forms. Once you have this disk that forms, these black holes that are found that deposit towards the supermassive black hole, they will be crossing the disk. And each time they cross the disk, twice per orbital period, they will experience a drag force, basically, friction due to the repeated crossing into the disk. And this will tend to align these black holes into the disk and embed them within the disk. Okay. The second ingredient is that once these black holes are embedded into the disk, we will have they will start migrating, just like planets migrate in protoplanetary disks. And if there is convergent migration, so if we have a positive migration torque here and a negative one, these black holes will converge toward a certain annulus, which we can call the migration trap. And for example, I can show you here if we calculate for a 10 to the 6 solar mass black hole with a disk around and the migration torque, you see that here the black holes will migrate inward, here they will migrate outward, and here inward, meaning that these black holes will eventually meet all together at the trap location. And then if the black holes meet while they migrate, we can have two-body interactions within the disk. So black holes may merge the gravitational waves or form a binary, a long-lived binary. And you can also have three-body interactions if you have a formed binary and meeting a single black hole, for example. And this interaction will cause some black holes to merge and then possibly be detected on the Earth. Okay. What I showed you right now is just it's a very sanitized and simplified picture. Actually, there are many sort of interactions that can happen in galactic nuclei with or without an AGN disk. First of all, there are interactions with supermassive black hole. So if you have a binary around orbiting a supermassive black hole, then you have the supermassive black hole exerting a torque onto the binary. This can accelerate the merger of inclined binaries. You have interaction with the AGN disk. So you have gas physics can induce, again, migration, but also these captures and also interaction between disks around black holes embedded within the main AGN disk. And of course, you have more pure dynamical interactions, which is single-single encounters or binary single encounters. And I should also mention that black holes may also form via star formation within the disk, not just be captured by crossing the disk, because we expect the AGN disks are unstable to gravitational collapse in the outer region. So they might just form there and then migrate inward. Okay. And yes, something that is still under scrutiny in these couple of years is the role of gas black hole interactions. This is still, I would say, unclear how they affect the evolution of black holes. There is now some hint suggesting that might actually accelerate and help the production of long-lived binaries if two black holes meet. But again, these are numerical studies with hydro simulation that depend on a lot of assumptions. And they might change it, so the results might change in the future. I will just now discuss a bit my ongoing work on this and plans on this astrophysical formation channel for gravitational waves. I will just mention this paper. It was actually a master student project that I completed myself after the student graduated. This other work that I did with a PhD student, I borrowed from some collaborators, and then some just mention one work I'm doing right now with another collaborator. And the first, the main paper I want to show is this is about three-body encounters in a disk. And just to show you the effect of three-body encounters, this is a visualization of a three-body encounter that can happen in a dense stellar environment. These are trajectories. A black hole binary enters from the right. A tertiary isolated black hole enters from the left. There is a brief chaotic evolution, and then eventually it can be demonstrated that you cannot form a stable triple. So eventually, this kind of system has to decay again into a binary, into a single. And it's possible to calculate what's the gravitational wave coalescence timescale of the binary. And in this very example, the coalescence time of the initial binary was much longer than the age of the universe, because it depends on the separation between the two black holes, the same major axis, but also on the eccentricity. And the final binary that kind of emerged from this interaction has a gravitational wave coalescence of only 2 million years, because the same major axis shrank and also the binary became more eccentric. So this is why three-body encounters are thought to be one of the main mechanisms to produce gravitational waves in dense stellar environments. Okay, and it's quite a standard picture. The main question of the project I worked on was answering the question how these kind of encounters differ from the one that happen in stellar clusters, differ from the one that may happen around a supermassive black hole, so maybe in an AGN disk. And the main difference, so here you have to imagine that there is a stellar binary, I mean a black hole binary, and a single black hole that meet while orbiting a supermassive black hole. The main differences between say the isolated case in which there is no massive perturber to the triple system is that there is, first of all, there is some constraints that the orbits are Keplerian around the supermassive black hole, and supermassive black hole exerts a limit, tidally limits the binary and the triple itself. Okay, and this kind of scenario is also relevant not just to AGN disks, strictly speaking, but also to disks of black holes found in galactic nuclei, because we do observe, for example, a disk of young stars in our galactic center. So one after these young stars, meaning actually massive stars, are gonna end their evolution. They're gonna become stellar mass black holes. So in our galactic center, we will have a disk of black holes eventually. And there are also a way to form disks of massive black holes in nuclear star cluster. So without the need to have an AGN disk, just to mention the relevance of this process. So the two aspects that I consider in this work is mainly two. One is disk velocity dispersion. So these are aspects that were never considered so far. And first of all, disks, just like star clusters, have a dynamical state given by the basically random motion of the black holes that are part of the disk, the objects that are part of the disk. We can have perfectly aligned and circular orbits around a supermassive black hole. This is a very dynamically cold disk. And if we increase, let's say, the level of noise, let's say velocity field, velocity noise in the black hole, this will become more and more thick and with eccentric orbit. So this actually can happen through if the disk is self-gravitating, so if black holes orbiting the disk interact among each other. And actually, this theory has been developed first to explain protoplanetary disk. And basically, we can describe the eccentricity and inclination of the orbits in the disk with the Rayleigh distribution. Is very intuitive. If you think about it, it's basically in a cold disk, you would have perfectly circular orbits, but as you add, let's say, a Gaussian noise, a Gaussian component onto the velocities in two directions, then of course you obtain a Rayleigh distribution. And the second aspect I consider is the supermassive black hole tidal field. It again was not considered so far. And in order to understand,
sorry, Alessandro, can I interrupt you? Can you tell us what dimensionless velocity dispersion means?
Yeah, yeah. Dispersion is basically if you take all the difference in velocity among stars, for example, they have. I can say it's basically the root mean square of the velocities of stars in an ensemble. So, for example, for star clusters, it basically characterizes how fast, relative to each other, the stars move. And in a disk is a bit different because the disk has coherent motion. So in a star cluster, the stars are randomly oriented, and in a star cluster, they are self-gravitating. So basically, they move in the mean potential of all the other stars. While in a disk, there is a coherent motion. So basically, the dispersion of a cold disk, where the stars are perfectly circular and aligned, is only given by the Keplerian shear. So different orbits, since they're all circular, they will go at a different velocity, just due to the Keplerian shear, just to the fact that the one that are closer, they orbit faster, and the one that are farther out, they're slower. So that's why this basically Keplerian shear is what dominates the dispersion, so the difference in velocity between stars. While as we add this kind of, if the stars become more inclined and more eccentric, then the difference in velocity between stars is actually due to this random motion, basically, and which is more similar to the random motion that we have in stellar clusters, for example. Okay. And this is important. Sorry.
No, go ahead. Okay.
Okay. This is important in regards to, for example, encounters. So basically, difference in velocities between objects in the disk is what determines the relative velocity when they meet, be them binaries or singles. And for example, if the disk is hot, so let's say it's dominated by random motion, the relative velocity will be very high. So the encounter duration is also very short, it's more impulsive. And there is also less chance for let's say, for a merger to happen, if you're looking only at gravitational waves, let's say. While if the encounter is cold, so let's say we take two objects and we let them free fall to each other, let's say there is the velocity between them, the velocity difference between them is very, very small, then there is more likely chance to have a collision, in a sense.
Okay. And what is X in the distribution you looked on?
It's just it's either E or so it's either the inclination or the eccentricity.
Ah, okay.
Yes, yes. And sigma is basically just dimensional velocity dispersion that can be characterizes the distributions of eccentricity and inclination in a randomly or random motion dominated disk. Yeah.
Okay, thanks.
Yeah. And the second aspect is supermassive black hole tidal field. Yeah, in order to understand better, it's better to kind of focus on ourselves on the co-rotating frame. So this figure is actually made for Sun, the Earth, and has masses around the Sun, but it can be applied also to a supermassive black hole. And the Earth here, it should be actually the triple system itself. And L1 and L2 are the Lagrange radii, where basically the potential well, where test masses are bound to the Earth, opens. And we can see that basically one effect that this configuration can have on the encounter that happen within this region, which is called the Hill region, especially in planetary physics, is that this Hill region will limit the volume where the encounter can happen. And I can, for example, visualize here in a very crude way that if we have a three-body encounter between a triplet of black holes, you have a chaotic evolution, and then you have some kind of excursions between the single and the binary. And what happens is that if the single strays a bit too far from the center of mass of the triple and the binary, it might actually cross the Hill barrier and be stripped, and so be captured by the supermassive black hole. And so my initial idea was that this tidal field actually limits the duration of these three-body encounters, and so it should actually produce less chance for collisions or gravitational wave mergers to happen. Okay. But on the other hand, what I actually found out later is that is the Hill region also traps the bodies within itself. And to show it a bit better, I made, okay, in this cartoon, for example, what will happen in reality is not that these stars will kind of escape and cross the Hill barrier and be lost and be captured by supermassive black hole, but actually it will bounce back and bounce back in the Hill barrier. So this kind of potential lines. And to visualize even better, it can be, for example, do a very simple experiment by taking the Earth, Moon, and Sun system, center onto the barycenter of the Earth and the Moon. And if I were to take the Moon and just nudge it a bit, make it more eccentric, so they would actually leave the Hill sphere, or the Hill region of the Earth, you would see that actually the Moon doesn't leave let's say the potential well around the Earth immediately, but it lingers around and it explores the Hill region. It may even do some flips and change the direction of orbital motion until finally finds the Lagrange ranges where the equipotential lines open, and then escape and become a planet, essentially. So this is, if with some imagination, you can replace the Earth and the Moon by a triplet of black hole and basically see that it will actually enhance the chance for collisions and mergers between black holes. Yeah, one last visualization about this problem. So unfortunately, this problem is a bit complicated, too complicated to be dealt with analytically. So we have to run simulations, and I did with my code called Tsunami, because of tidal evolution for stars. That's another story. And if we were to visualize actually the trajectories of these black holes around the supermassive black hole, it would look a bit like this. I have scaled up the z direction to kind of magnify, see better the interaction. So here we have a binary black hole and a single star. They meet here. They undergo some. These are what I called earlier excursions. You have this moment which all the three bodies are within a small region of space. They're interacting, and then eventually you have a last exchange between the bodies. You have an ejection, and then there is an escape. And actually, what happened in the end, there is even an exchange between so the final binary is different. The members of the final binary are different from the ones of the initial binary. Okay, and I just want to show one result. Is that basically this plot shows the merger efficiency as a function of decreasing velocity dispersion. So this actually here is a perfectly circular and perfectly circular and aligned orbits between say black holes and binaries, while here is a disk that is dynamically old, and so it's quite everything is quite thick, as orbits are inclined and eccentric. And this actually captures the transition between a disk that is dominated by Keplerian shear and one is dominated by random motion. And what you can see is that basically the dispersion crucially affects the merger efficiency. It can be higher, much higher in a dynamically cold disk by a factor of 43. Many mergers are actually are eccentric. So by calculating, let's say, propagating the orbit solution down to when the gravitational wave emission, the peak of the gravitational wave emission, because when black holes are eccentric, actually the gravitational wave spreads among many frequencies, but taking the peak of the gravitational wave of peak harmonic in amplitude, we can see that many of these black holes, binary black holes, are actually eccentric the moment they enter the detector frequency at 10 Hertz, which is the beginning at which is a design sensitivity. And this dotted line here is the merger efficiency for a nuclear star cluster without a supermassive black hole. So there is no disk. The orbits are randomly oriented, and there is no black hole. There is supermassive black hole, and basically the merger efficiency is much smaller. Because what happens is that the fact that there is coherent motion helps to basically decrease a lot the velocity, the relative velocity between binaries and singles, while in a randomly oriented star cluster where there is no coherent motion, you have much higher relative velocity when during encounters. Okay. So in this work, I just explored, let's say, the effects of the velocity dispersion, but actually I hadn't tell you what actually is the velocity dispersion.
Can I ask one question about
Yes.
the previous plot?
Yes.
So is this for an encounter or for a statistics of many encounters?
This is a statistics of many encounters, many binary single encounters, yes.
Because I would imagine that sometimes it could make it more efficient, sometimes less efficient, or does it always make it more efficient?
No, this is an average over 500,000 realizations. So there are many kind of random parameters. For example, what is the phase of the binary at the beginning? What is the impact parameter between the binary and the single? And averaging over these parameters, well, not averaging, sampling these parameters and then calculating the merger efficiency, which is basically the fraction of time a merger happens during the simulations. Then I can calculate this efficiency, yes.
And it's chaotic, right?
It's chaotic, exactly.
I change a bit the parameters, so it will be very hard to average, or no?
Well, it's chaotic, but converges statistically. So if you, let's say, if you fix, let's say, the properties of the encounter, and then you random sample the one that can be, let's say, sample like the binary phase, things that we expect to be random, then you can see basically that for example, the merger efficiency, but also other, if I were to draw a distribution of what is the final distribution of, say, major axis of the binaries that do not merge, for example, the distribution would converge eventually. Of course, if you have too few samples, there wouldn't be any it would not be statistically converged.
But okay, can I ask a question? So are these three-body encounters a curiosity, or do they happen?
What do you mean curiosity?
Now, are they a theoretical exercise, or does it happen a lot in nature?
No, it happens. It happens. Is the main, I would say, among the dynamical channel, is one of the main mechanisms that we expect to happen at the center of star clusters. And I have some other slides, not in this presentation, but basically, star clusters do exist, and we observe them, and they evolve through gravitational, relaxation, two-body relaxation. So basically, long-range interaction between stars have induced a kind of a secular long-term evolution of this star cluster. And the evolution is that the center of the star cluster collapses, and the outer outskirts, enlarges. Okay, and as the core of the cluster collapses, it increases in density. So the higher the stellar density, the higher the chance for these three-body encounters to happen. And actually, three-body encounters at some point, they need to happen in order to lift this collapse of these stellar clusters. So this is the kind of the standard picture for three-body encounters. Actually, they were proposed at the beginning not as a way to produce gravitational waves, but as a way to basically control the evolution of stellar clusters that were mostly studied in the 70s. And in a disk, it's slightly different. So here there is no the instability that causes an increase in density. This is just because, for example, black holes do migrate. If there is a disk, if they migrate, they will converge to the same location and then undergo an encounter. If it's a dry disk, you might just have overlapping orbits. And if the orbits do overlap, then you have an encounter.
Can I ask a related question? So you say that these curves are the result of an average, right? It's for this kind of chaotic things. Is the mean a representative quantity in the sense, let's say the distribution is sharp enough that?
If I were to plot the say Poisson error in this plot, it would be less than the thickness of the axis.
I see. Okay.
Yes.
I see. Okay, so the mean cioè, let's say the distribution is not, let's say, fat-tailed or something that makes the mean not particularly representative. I see. Okay, thanks.
Yep. Yeah. Okay. And yeah. Oh yeah. Something I didn't mention earlier, like is like what is actually the velocity dispersion. So if the velocity dispersion affects a lot the merger efficiency of the body encounters in a disk, what actually it is the dispersion. And this actually crucially depends on the origin of the disk. So as I said, we might have formation of disks in dry or quiet galactic nuclei. So there is a supermassive black hole, but there is not an AGN disk. And for example, if there is a molecular cloud that falls into the around the supermassive black hole, and it will form a disk that looks a bit like this. So you have eccentric orbits, but they're also aligned pericenters. There's also another process which I won't describe that might produce eccentric inclined disk. In AGN, coming back to the AGN, we expect that dynamical friction, gas dynamical frictions should circularize our orbit while they, for example, they cross the disk. But there are some caveats. So first of all, there will not be enough time to fully circularize the disk by the time the AGN expires. So AGNs have a duty cycle, so which is expected to be say tens of million years. So if then the disk disappears and the black holes haven't circularized or embedded into the disk, then there won't be any of this process. There might be also two-body interactions, gravitational interactions between the black holes embedded in the disk that might excite eccentricity. And another aspect I consider is that AGN disks are actually turbulent, and this may actually counter dynamic gas friction, which is the process that leads to the circularization and embedding of the black holes. And just a brief recap on dynamical friction. This is a process that was first studied by Chandrasekhar, and it's basically an effect of a massive particle that is moving across a medium of less massive particles. And it's basically can be described as a drag force experienced by the massive particles due to the fact that as the massive particle moves, there is a wake, density wake, over-density wake that forms behind the massive particle. And this over-density tends to slow down by gravitation, the massive particle. And this works in stellar medium, but also in gaseous medium, so collisionless and collisional. And so this is the main process that should circularize and embed these black holes inside these AGN disks. However, AGN disks are turbulent, and because we need this turbulence because AGN disks are accretion disks. We need to have mass advection within the disk, which is due by kinematic viscosity. And the molecular viscosity has been shown not to be enough to cause, let's say, the accretion rate to explain the luminosity of an AGN. And we think nowadays that this viscosity arises from macroscopic turbulent motion and possibly powered by a instability of gases, magnetized gaseous media in a differentially rotating disk. And if basically gas friction is very efficient, what I consider that, so there is a tight coupling between black holes and the gas flows. And if these disks are turbulent, so we have very large scale turbulent flows, the black holes that are embedded might actually follow and be dragged around by the large scale turbulent eddies. And an analogous problem is, let's say, again in planetary physics, is dust grains coupled to the gas by aerodynamic drag in this case. And I did this very simple modeling, and I don't have time to explain all the ingredients I put into this. This is a numerical model, but basically you see I put a black hole around a AGN disk close to the migration trap, and I let it with this black hole as this kind of same major axis, eccentricity and inclination, which are greater than 0. And if I don't include turbulent motions, this black hole will slowly decay and become completely embedded into the disk and also fully circular. So extremely cold. But if I add on top of the, say, gas velocity, a turbulent turbulent velocity field, basically what happens, so these are 150 realization of the same evolution, except that I added different realization of the turbulent field because it's now stochastic, yes. And what happens that the eccentricity inclinations plateau around some values, because this is basically a limiting value due to the, it can be shown that this corresponds to the variance of the turbulent velocity field. Okay, this is a work I've been working on right now, basically. For example, this work I've done, dynamical friction, gas dynamical friction depends a lot on the details and thermodynamics of the AGN disk. And so this would have not been possible by this other work I've recently put on the archive, PhD student, which is basically a critical analysis of one-dimensional AGN model. So we need, in order to use, for example, these dynamical friction models, we need to have a knowledge of what is the structure of the disk, including what is the density of the disk as a function of radius, what is the, this is just the gas pressure over total pressure, so the thermodynamics of the disk. This is the opacity, which has an effect on the, again, on the structure of the disk. And so we put out this work on the AGN disk models. When the AGN disk models are now using to model and to know the disk. So this AGN disk structure. This was actually the first open source implementation that we even published with a Python package. And now I'm working with collaborators on improving these models by adding these models are stationary, so we assume there is a steady state accretion flow, but the idea is to make them more complicated and to add, for example, non-stationary, so time evolving AGN disks, and also include an additional energy source that is accretion luminosity from embedded black holes. This is not considered. So eventually, this is basically what my research is going to, at least in regard to gravitational waves. This is having a comprehensive model of AGN disks and their surrounding black hole population in order to obtain constraints on black hole observables, so rates of black hole mergers, masses, and spins, but also relation to AGN properties, which is supermassive black holes mass, accretion rate, viscosity, provide prediction for future detectors. But the second point is also quite interesting in the sense that we have not, very few people have, actually nobody so far have discussed what is the effect of these black holes on the global AGN disk structure. So for example, if black holes that cross the disk are many, then they will have an impact on the local thermodynamics of the disk when they cross the disk, for example. Or if the black holes are embedded, they will have an accretion luminosity. This will change the global structure of the AGN disk. And this is still unexplored phenomenon, and that I would like to explore. Yeah, some numerical models. And okay, final, moving a bit out from gravitational waves and EGNs. What the rest of my research is actually on the Triboli problem, the gravitational Triboli problem, and application to astrophysical scenarios. So I showed you one, but there are actually many others. Some of them include another, again, for gravitational wave astrophysics. Some of them are more to fundamental problems like stability of triples or constraining binarity. Let's say trying to observe triple black holes in a triple with observations or other kind of aspects. And I also do work on more fundamental problems of the gravitational Triboli problem. This is really not about astrophysics, it's more about trying to find a solution, statistical solution of this 300-year-old problem. And recently, I put this manuscript on the archive. It's basically, long story short, is since you also mentioned chaos earlier, the three-body problem is indeed chaotic, and we can use chaos to motivate statistical theories. We call them statistical escape theories, to basically provide a stochastical description of what are the outcomes of three-body problems or three-body interactions. And these theories are based on the ergodic principle, which assume that the phase space of the three-body problem is completely mixed by chaos. Okay, so what I show basically in this paper is that actually the phase space of the three-body problem is a mix between regular, so non-chaotic regions, and chaotic regions. So this impacts the efficacy of statistical solutions. And it's also important for if we want to use this statistical solution for astrophysical problem, because they will predict the final outcomes of chaotic regions, but they will miss the outcomes of regular regions. And I also did a series of papers with the undergraduate student who is now a graduate student in Stanford. Yes. And yes, on this topic, actually, there is a YouTube video that kindly recorded by Monash on a visit I did in December on exactly this work. If you're not tired of listening to my voice, you can find it on the Monash University channel. And together also with Monash, I'm organizing a conference on the theories of the three-body problem. It's going to be a conference for all problems related to all applications of the three-body problem. So it's going to be very interdisciplinary. We will have relativists like Cliff Wheel, mathematicians like Richard Montgomery, who is the one who first characterized the figure of 8 solution of the three-body problem. Konstantin Batygin, proposer of Planet 9, the solar system, and Joseph Monocan, the professor who started the whole statistical approach to the three-body problem. Okay, with this I finish. Yeah, one last advertisement is that I recently came in charge of the Gravity Seminars at the Niels Bohr Institute. So we are very interested in the works on gravitational waves. Yes, and so if you happen to be in Europe and you want to extend your visits, you can contact me or some other person of the GW Astro group, and we can take care of accommodation and flights. Yes. Okay, I finished now.
Okay, thanks very much, Alessandro. So we have time for questions. So who wants to start? Rogerio, go ahead.
Yeah, actually, this is Riccardo Strani, by the way. Nice to meet you. I'm slotting Rogerio's connection.
Yes.
So that may be provocative. I mean, is there any hint that any of the 90 confirmed LIGO virtual detection came from a three-body process?
Yeah, so at the moment, there is no... So, yes, this is like, okay. At the moment, there is no consensus of from where the gravitation, these 90 events come from. There are some, just by looking at the population, we can have some estimates of, for example, what are the properties of black holes from different scenarios should be. And let me, for example, show you. So we say three-body encounters, but here there are very different scenarios where three-body encounters operate. So one, as I said, is the AGN channel. And for these, the estimates stand like these. They're quite uncertain. So the current binary black hole rate, for example, is this one. There has been some estimates of what is the rate of the AGN channel using a Drake-like equation, and it's highly uncertain. And if one takes into account the uncertainties of all these parameters, which include how long an AGN is on, what is the number of captures the AGN should have, and so on, the uncertainty is very high. So we don't know yet. Then, of course, we can besides the ray, we can have a look at the population properties, okay? And I don't think I have any slides of this in this presentation.
For instance, I mean, can you justify 30 solar mass peak in the math distribution?
No,
Like
I think as far as I know, there is no model that can justify the 30 solar mass peak. Yeah.
So, okay, so at the end of the day, how you can hope to constrain the AGN channel contribution?
By studying, by basically, for example, let me see. By studying what are the properties, and for example, no, let me think. What is this? Yes, okay. So we have already some idea of what are the properties of say sources coming from the AGN channel for what are called Monte Carlo models. So here they basically use a parameterized approach to describe the physics, while I would like to do some more detailed model that includes post-Newtonian evolution, of the sources. So we basically expect these three main evidence: high eccentricity. We should see also masses in the pairing stability mass gap, because we expect repeated mergers. So the merger product should be remain embedded into the disk, and also see some mass spin correlation. And if you look at this last point, there is an anti-correlation between binary black hole mass ratio and effective spin in the current gravitational wave data. That said, I personally don't think that any of the current mergers actually come from this channel, because I think that this channel should be so AGNs, the density distribution of AGNs peaks at redshift 3, and we see we are only sensible to the local universe at the current observations. Of course, the situation will change in the future. And that said, I do think that this process is quite inevitable. We expect to see AGNs, black holes at the center of galaxies. And let me show you these other slides. Yes, this one. So we do expect that black holes to be found at the center of galaxies. We do expect AGN disks to form. So I think that if we constrain at least what are the properties of these black holes, or even if we say that that these mergers are the merger rate is too little, it's already something that we can use to constrain AGN physics as well.
Okay, but you said something interesting, no? Is that this mechanism should be effective at higher redshift. So, I mean, forget about gravitational wave. Can you envisage some other way to probe these mechanisms? Like, for instance, now we know the supermassive black holes are formed a bit earlier than we thought, even just 2 years ago. So can this mechanism be able to dissipate more? I mean, it's funny to talk about gravity as an efficient way to dissipate energy, but I mean, it might play a role, no, to trigger, to enhance, to speed up the formation. Did you study this? Is it a viable line of research?
You mean dissipations due to gas interactions? You mean?
No, really, multiple body encounter. You know, in the protogalaxy, in the center of the protogalaxy, there might be multi-black hole, multi-star encounter, and then that could enhance wildly the number of coalescences, and pulling them to time scale much smaller than the age of the Newton. That could have played a role in the early formation of the central black hole of the galaxies. Is this something crazy or something that people thought about? Or?
I think I never heard anybody talking about this. So you mean more when the black hole supermassive, really the formation, for example, when you have protostars or supermassive stars that collapses into a supermassive or an intermediate massive black hole. Is this what you?
Yes, but this doesn't seem to be enough not to create the supermassive black hole that we are starting to see recently. I mean, we need some other mechanism to speed up their collapse.
To speed up. Of course. Yeah, so one aspect is, for example, so we don't have precise constraint on how much these black holes are embedded into, I mean, the black holes that are embedded into the disk accrete, for example, and if they actually, we manage to reprocess the accrete, the gas in the disks, they might be able, and then might be able to migrate closer to the supermassive black hole and do an extreme mass ratio spiral. This would be a way to feed the black hole mass with the, instead of using gas, would be with gravitational wave mergers. This is not strictly a new idea. There is a runaway process of supermassive black hole formation from basically IMBHs, intermediate massive black holes. It's one of the main scenarios. The difference here will be that it's actually stellar mass black hole, and they migrate and they accrete thanks to the interaction of the GN disk. I don't think it's a crazy idea, but it should be careful when characterizing the gas interactions, because we have very few constraints on how much for example, these black holes embedded into the AGN disk can accrete, and how even the gas plays a role in the black hole interactions. Yeah.
Okay, sorry, and then I will stop monopolizing the question session.
Okay,
so,
okay.
There are a few outliers, no, in the LIGO. I mean, a few strange masses in the LIGO detection.
Yes.
The high mass gap, the low mass gap. So, can you quantify the rate of recycling? Saying how many binaries we should be seeing that are recycled, that are recycling the merger of a previous collapse of a previous merger?
So the fraction of hierarchical mergers, you mean?
Sorry, the fraction?
You mean hierarchical mergers?
Yeah.
I would say, so what I cannot say, because I haven't, so this is not work I've done personally, but what some people have done, again, with these Monte Carlo models, is by parameterizing the efficiency of gas hardening, so the efficiency of how the gas impacts the evolution of binaries.
No, I'm talking, the outcome of a merger that is caught in another binary. That actually form another binary.
Yes. No, I haven't. So in my work, I only consider a single encounter. So it was only the effect of a single encounter. So I didn't, let's say, continue the evolution with the merger product.
Yeah, but there are few events in the LIGO catalog that could point to this exotic possibility. But the problem is
possible.
Maybe even 1 in 100 is a bit too much, right?
Yeah, it's a possibility. I would say maybe I think the spin is the most critical aspect of these hierarchical mergers. It's a bit poorly constrained. That's the main problem. And again, this is not unique at the moment. Hierarchical mergers, even in a star cluster, will result in some correlation between the spin and the mass of the stellar mass black holes. And simply just because as you build up the mass through repeated mergers, then some of the spin will be some of the angular momentum of the binary at the moment of merger will become the spin of the remnant. So if you're asking me if it's possible that some of events, like say outlier event, like mass gap event, is due to the AGN channel, I can say yes, but so is any other channel that predicts mergers in the mass gap.
Okay, thank you.
So I have a quick question, Alessandro.
Yes.
Very naive question. So usually I don't work on gravitational waves, but I know that in order to identify masses and spins, etc., of these mergers, you need this bank of waveforms.
Yes.
So my question is if you have a three-body system, if this will change the waveform.
Yes. Yeah. So we're actually studying this right now. So what you can have is a phase shift. So you have some effect. So first of all, you have the fact that the binary is perturbed by a tertiary object, and it's actually moving. So this will induce, let's say, a delay shift in the wave. You also have the effect of the gravitational force, so the tidal force of the tertiary onto the binary. So this again induces some perturbation on the waveform, and then of course, yeah, and these are the two main effects basically.
So is it possible that since the bank of waveforms is only for two-body coalescence, is it possible that the detections give you the wrong values of the masses because of this effect?
It's possible that there is a bias. Yes, it's possible that there is a bias in the inferred properties. So this aspect is actually studied a lot in the LISA community, because we expect environmental effects to be more detectable, because if you have a almost monochromatic source, and you have gas interaction that will modulate the phase of the binary, which will include a phase shift into the waveform. And I think that they definitely can impact the how can I say? Yes, the estimated parameters. I wouldn't, from the top of my head, I wouldn't be able to say how they would bias. What we are pointing right now in some paper is that there is a phase shift. The one in principle should be able to detect. Unfortunately, not in LIGO, Virgo, or Kagra, but we need to wait for third generation detector like the Einstein telescope. Yeah.
Okay, thank you.
Yeah. The potential for this is really be able to constrain on a single event what's the origin, just because you observe the phase shift due to the tertiary object.
Yeah. Okay, thank you, Alessandro.
Any other questions for Alessandro?
Well, perhaps a very simple question. I mean, I understand that your research is highly driven by numerics, right? I mean,
Yeah.
You also prepare packages in Python to. Can I ask you, under the hood, you use for that?
C++.
I see.
Yeah.
I see. And these kind of computations usually, I mean, they run on let's say GPUs or clusters or.
So for the things I do, I use CPUs because I have very low number of particles, let's say up to 100. So I don't need to parallelize the process. No.
I see. So it's not parallel. I mean, it's.
No.
I see. Okay. So you parallelize, as far as I understand, you parallelize on the initial conditions, right?
Exactly. So it's like a embarrassingly parallel problem. So I just need to increase the sample size to have a statistics, because the system is chaotic. But then I just need to parallelize the individual realization. Yeah.
Okay. Yeah. I see. Another really, can you go to the slide in which you introduce the three-body encounters? I mean, it's curiosity dictated by ignorance.
Okay, so no, this is this one or
the one I think at the beginning.
The one with the scheme, with the trajectories.
Yes.
This one.
Yeah. I mean, here is really. I mean, essentially, I mean, they arrive from far away. They interact for a while in a very chaotic way, and then they escape from chaos again. How this mechanism happen? I mean, how a system once entering a chaotic region escapes and go again to a non-chaotic situation? It's
well, so I mean, like physically, or more like.
I mean, it's more a question like really about let's say chaotic dynamics. I mean, how a system escapes from.
Okay, so so you can. So what happens that basically to a binary and a single meet. So they have initially some hyperbolic orbits, so they are unbound with respect to each other, and then after, say, the binary breaks, the hierarchy of the system breaks. So you have a chaotic motion, and we usually describe it in two different phases. Again, I have some slides not in this presentation. It's basically a chaotic phase. We call it democratic resonance, where all three bodies more or less are in the same volume. They're interacting, and they exchange energy, angular momentum freely. And then you have other phases, like let's say this one here. So this ellipse here, in which there is a momentary ejection, not really ejection. Yeah, it's an ejection. Let's say, call it an ejection, but the binary and the single are still bound to each other. And after they come back, they're gonna again undergo a democratic resonance. And this process can basically continue for an infinite amount of time. In principle, is not really bounded. But of course, it's unstable. So the system is unstable. It can be shown that the lifetime of these systems is like decay exponentially and then become a power law. And then basically, though you cannot form a stable triple in this due to this process. And I think the easiest way to see it is that a stable triple should be stable both in the future and in the past. But if it was formed, so Newton equations are reversible, right? Time reversible. So if this system was formed by a chaotic interaction in the past, then the stability is not guaranteed in the future.
Right. I see. But so let's say the trajectories of when, let's say, one goes in one direction and 2 and 3 goes in the others, the direction of this motion is highly sensitive to the initial conditions, I guess, right? Because that is what makes the system chaotic, right?
Yes.
I mean, okay, I see.
Yes, not completely chaotic. So there are actually some regular regions in which, so regular interactions, they have a finite size in which the system behaves regularly.
I see.
And is not chaotic. It's obviously not this example, but it's in basically is the main point of the paper I showed at the last slides, basically.
Okay. Yeah. Thanks.
Any other question?
So, just curiosity, this three-body dynamic code, does it include dissipation, gravitational wave dissipation? Or...
Yeah. Includes, let me see if I wrote it somewhere. Yeah, post-Newtonians, corrections up to 3.5 pm. And also spin-orbit coupling due to spin-spin and spin-orbit interaction.
Also in luminosity, also in the flux.
Sorry?
Yeah, also in the flux, yeah, dissipation.
In the flux.
Or just the conservative dynamics?
No, the 2.5, yes, is included. The 2.5 and the 3.5, yes. So there is radiation, yes.
Any other questions?
Sorry, maybe just a very naive one. So do we measure, we have these three-body encounters and then two black holes merge and we measure that, right? We don't measure the gravitational, or do we also measure the gravitational waves coming when the three bodies are interacting with each other?
No, so what we measure, I mean, observationally, we measure only two bodies that merge the very last instance. We are actually, yes, thinking about computing what is the gravitational wave bursts that may happen during an encounter. So between all three bodies. I think one can expect that this will be very, very not loud. So because generally speaking, so if two bodies get too close to each other, they will rapidly spiral and merge. So eventually you're again in a situation where you have a binary in spiraling and we perturbed by a tertiary body that is just happens to be there during the interaction. What can happen is also this kind of gravitational wave bursts, and some people I think have been discussing this, but I haven't seen any paper out yet on this topic. That's during the interaction, of course, you have some small gravitational wave radiation that is radiated by close passages that are close enough, not close enough to cause an inspiral, a rapid inspiral, but also they're not wide enough so that there's basically zero flux of gravitational wave radiation. I think that the interesting parameter space to be a bit fine-tuned, very limited, because much more easy so the impact, let's say the impact parameter you need to have between two black holes, it's should be quite small in order to see these to observe these bursts of gravitational waves. Yeah.
But then if you just measure the very end, I'm a bit lost. So this gravitation, sorry. Yeah, my question is, if we only measure the very end, what we are trying to see is if in the past of the story of these two black holes, if they encounter the third one, maybe once, maybe twice, maybe 3 times, but will this not be super hard to tell? Maybe
no, with the current observatories, definitely no. We need to go to lower frequencies. Yeah, we basically need to. We need to go to. Yeah. We need to go either to space for very low frequencies, or just maybe how to say, yes, basically space interferometers that can measure the signal when it's as a much lower frequencies. Yeah, currently with these interferometers that we have right now, we are only capturing the last instance of the spiral. So definitely these kind of environmental effects will be, they're out of the band, out of the observable band, basically.
I'm still a bit lost. So there are many things that could happen to black holes. One of them is these 3-body encounters, right? But
yes.
But
there is also
in the end, astrophysics is very messy, it's very complicated. Many things can happen, but we try to extract some physics out of it, and the more messy it is, the harder it is. So is the goal to find out contamination by some chaotic effects that we want to discard so that we study only the encounters that are purest and that don't have this garbage? Or do we like this garbage because there is some physical information there?
I think so. The main idea is to try to find where these events come from, and doing this by obtaining properties of say mock observations from known astrophysical environments and processes. This is one way. So just look at population-wide inferred parameters and compare them with the mock population-wide parameters. So basically these masses, these observables, and relations between these observables. And then of course we have environmental effects that we might impact on the waveform itself, and these could be detectable in principle, like the phase shift I was mentioning earlier, or let's say gravitational wave bursts, as you basically hinted to.
Okay, thank you.
Any other question? Okay, so thanks very much, Alessandro. So we still are going to talk to the search committee and interview a few more people, and then we'll let you know about the status. But
okay,
within a week, we'll certainly let you know.
Within a week, okay, thank you.
So thanks very much, Alessandro.
Thank you for listening.
Bye-bye.
Bye bye. Bye bye.